Hello everyone. So we are going to answer the question 8. In the question, we are given a spherical container with inner radius equal to 0.4 meter. The outer radius is 0.41 meter. The thermal conductivity K equal to 1.5 watt per meter degree Celsius. The power given is the power for the heater is 800 watt, while we are assuming that 10% of heat generated by the heater is lost through the insulation. And since the spherical container is insulated, the heat transfer coefficient H is considered 0. Then, before we started the calculation, we assume that the process is a steady state and no heat generation occur.
Firstly, we know that 10% heat is lost during the insulation. So, with that we can calculate the heat flux by using this equation. We know that 10% heat is lost. We know that there's 90% balance of the power generated. So we can use 0.9 times 800 divided by the area of the outer radius of the container. After that, we will get the value 340.8 watt per meter squared. The differential equation of this situation can be expressed as d over dr r squared dt over dr equal to 0. By using the information given, we can obtain the first boundary and the second boundary which is needed in the solution. The first boundary is TR1 equal to T1 is equal to 120 degree, which is given in the question. The second boundary is K dt over dr R2 is equal to the heat flux. Next, we will integrate the differential coefficient that we have obtained before. Integrate the equation as usual. We will get r squared dt over dr plus C1 equal to 0, and we will and the final equation is like this. After that, we will divide the previous equation with r squared, and then we will obtain this equation. Then we will integrate this equation. Integrating both sides, we will get T R is equal to C1 over R plus C2. Equating R is equal to R2 we know that dt over dr is equal to C1 over R2. We will substitute this one into the second boundary equation, which will look like this. K C1 over R2 squared is equal to heat flux. And then we solve for C1. After that, we know that R is equal to R1. We will use first boundary equation, which will look like this. TR is equal to T1 will equal to negative C1 over R1 plus C2. And then we will solve for C2. T1, and then since C1 is equal to this equation, we will substitute it here. Q as R squared 2 over R1 K. And then we will find, the question wants us to find the temperature of variation for this problem. And then after we have solved for C2, we will just substitute the equation into this one. And then the final equation is T1 plus 1 over R1 minus 1 over R times Q as R squared, R2 squared over K. Tak payah nampak ni. And then we will just substitute the value into the equation that we have obtained. As 1 over 0.4 minus 1 over R times 340.8 times 0.41 squared over 1.5. We will get 120 plus 38.19 2.5 minus 1 over R. So this is our final temperature of variation. For question C, it wants us to find the T for the outer radius. So we will note that R is equal to R2. We will just use the previous equation that we have obtained. TR2 is equal to 120 plus 38.19 times 2.5 minus 1 over R. R is the value for the outer radius, which is 0.41. And then we will get the temperature for the outer radius, which is 122.3 degrees Celsius. Last equation is, it was asked that how much water at 100 degrees Celsius can the tank supply if cold water enter the tank at 20 degrees Celsius. So now we want to find the mass. And then after we arrange the equation, it will look like Q over Cp delta T. The value of Q is 0.45 kilojoule per second. Divide by Cp, that can be calculated, 4.815 kilojoule per kg Celsius. And the delta T is 100 minus 20. We will get the mass as 0.00134 kilogram per second, and we converted it to per hour, and we will get 4.84 kilogram per hour.
That's all from us. Thank you.